How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the work of the young Frenchman Blaise Pascal, a genius of the 17th century, who died at an early age, indeed at 39, but left enough for us to contemplate for a lifetime. And I urge you to read his life, written by his sister, La vie de Blaise Pascal, the life of Blaise Pascal. Indeed, at the age of 12, he happened one day to strike a dinner plate belonging to his mother, and it rang out, and he was thus led to write a definitive paper on vibrating bodies. I urge you to go read about him. Now, one of the principal things he had concern with was the property of liquids and of fluids, and raised a very interesting problem. Consider, let us get a picture of him. Here he is, just some few years before his death. Blaise Pascal, a genius of the 17th century. Consider the following. Supposing I have a vessel shaped like that, another one with the same base shaped like that, and another one with the same base shaped like that. Three identical vessels, that is, the bases identical, and now I fill them with water to the very same level. Water, water, water. Question: on the bottom of which vessel do we have the greatest force? Answer. Discussion. Most water here, most mass of water, most weight of water. The bottom here supports all the water bounded by those vertical lines. The bottom here supports the water bounded by those vertical lines. The bottom here supports the water bounded by those vertical lines. Well, says somebody, I see water in here and water in here. What holds that water up? Answer: the sides. Then somebody says, there's no water in here and no water in here, and yet the push on the bottom is the same. Answer: yes. Reason: the walls push in with a force which compensates for the water which is not there. And I'm going to show you this with a wonderful experiment. Here it is. Here it is. Here is a narrow-walled vessel, and I'm going to fill it to a certain level by raising a chamber of water. Here comes the water, here comes the water, there comes the water. Hold it, right there. I'll get the water level in here proper as measured by the position of this marker. And if we read the scale, it reads about 43 or 4. Now I'm going to let the water run out of there and replace this vessel by a very big one, quite like the middle vessel that I drew on the board. And I hope you see that this vessel is vastly bigger than this one, but they have the same bases. They have the same base. I'm going to screw that on there, if I can do it here. There we go. And now I'm going to raise the water in here to the same level as in the other one, and I hope you will see that the gauges read the same. There's always a little trouble with the linkage system in such a mechanism, so there may be a little trouble, but I'm bringing the water up to the same level. Since the sides are flared out, the rate of growth of depth is less, but there we have it. I've exceeded the level a little bit. I'll come down a little. I'll come down a little. And I think that's evidence enough that the readings are identical. The readings are identical. Amazing piece of business. Consider another consequence of Pascal's work. Supposing I have a little chamber here connected to a big chamber here, and I put a piston in this chamber and a piston in this chamber, and this is filled, of course, with some incompressible fluid, oil or water. You are aware that if I push down on this piston, the water goes up there and lifts that piston. This is an hydraulic press. If indeed I make this a compound machine by attaching a lever in this manner, and I apply a force here, I can pump the liquid from here down and lift an enormous load. Indeed, if this piston is very small compared with that one, I can multiply the force I apply here, depending upon the length of this lever, thousands of fold. And I'm going to show you that. Here I have such a system. Here I have such a system. A little piston right here, and a big piston right there, and here is a block of wood. Here is a block of wood. And I say it takes about a ton of force to break that wood, and I can't do it with the unaided hand, but let me put it in there. I made a little mistake. I have to come down a bit. Watch it now. Watch. I am going to deliver. And here is what I wish you all to see. That with ever so tiny a force applied out here, with my little finger, I can produce a force of about 1 ton at the middle of the board above this piston. Watch it now. Watch the scale. Oh, well, this board broke at about 1/2 ton. Now, you know very well that I could not exert a force of 1/2 ton with my naked hands. Here is a board, a piece of 2 by 2. I would say that it will take about 2 tons to break this. About 2 tons. Now watch it. This is fantastic. Applying Pascal's view that the liquid is incompressible and any small force applied here is felt without loss in all parts of the machine. Watch it now. There it reads 1.5 tons. There, it fractured at something around 1.5 tons. And I say that is fantastic. Oh, staggering, staggering. The forces which we can impress here. Now, I could show you another experiment with that hydraulic press. Here is a spring. I will not pursue the adventure, but this spring has an enormous modulus, meaning that it takes extraordinary forces to squeeze it together. More than 2 tons, in fact. I couldn't do it with the naked hand, but there I could do it very easily. Let us consider another consequence of Pascal. Here's one of very great usefulness to the human race. Here is a hypodermic needle. Question: why is the needle sharp, very pointed? Answer: for the same reason that you wear snowshoes to cross deep snow. You spread your force out over a large area, so the pressure, which is the force per unit area, is very high here in the needle. For example, ladies with high heels. A little girl weighing 100 pounds can leave more impression on an earth road than an elephant. Imagine that. Why? Because her weight is on so small an area. So here we have it. I push with a force of 10 pounds with my thumb. The hypodermic needle has a pointed area of about 1,000th of a square inch. The pressure is 10,000 pounds per square inch. Fantastic. Fantastic. Consider another one. This is beautiful. Here I have a flask filled with colored water, 1-hole stopper in a glass tube. And I call your attention to the level of the water right here. I hope you can see it. The level of the water right there. A little difficult. There, that's very good. Beautiful. Now what am I going to do? I'm going to squeeze on the wide sides of the glass. And we see an astonishing thing. Watch the level of the water. Watch it. There it goes up. Suggesting 2 things: that the glass is very elastic and the water highly incompressible. Another adventure with the same thing. Let me turn the glass sidewise. Let me squeeze on the narrow sides. Question: what will the level of the liquid do? Answer: when I squeezed the wide sides, I deformed them inward, diminished the volume of the vessel, and up went the liquid. When I squeeze them on the wide sides, will I not bulge out the wide walls, and will not the liquid fall? Watch it. There it is. It goes down. Another adventure which you can pursue, the Cartesian diver. Here I have a little creature in the shape of a man in which we have put some water, and he floats at a certain position. There is some air above the column of water. There is some air in him. What am I going to do? I'm going to push down on that rubber sheet here. That force by Pascal is communicated without loss to all parts. The water in here feels it. The water in him feels it. The air inside of him feels it. And because the air is compressible, it gets compressed, more water goes in, and he goes down. So you see, it is not me pushing that pushes him down. It is this sequence of actions. Watch it. There it is. I love that little business. And, whoop, I can stop him where I want. Since they are differently loaded, they ride at different positions. Now you can make one very easily. You don't need such a thing as that. A little medicine vial would do, such as little pills and the like come in, and here it is. Here it is. There it is. Like a submarine, in fact, exactly how a submarine works. I release the force or the pressure, and up he comes. Consider another consequence. Let's go over here, back to this table, because there are some enchanting things. Here is an experiment which we could do, but we will not. We will consider it a virtual demonstration. Here is a flask, filled completely with water, completely, with a tight-fitting stopper. Liquids, I say, are incompressible. Conclusion: I can deliver a sharp, impulsive blow to that stopper. So, that force would be felt in all parts of this chamber, and it would burst into a million bits, and the water and glass scatter. Enormous. Why? Because Pascal said any force delivered to a liquid is communicated without diminution, without any lessening, to all parts. Another one of the same kind. Here is a wooden block with some nails in it, and here is a flask. Unfortunately, this flask has a bubble in it, which I think you can see. And bubbles of air are highly compressible. I cannot, therefore, do what I want to do. But supposing I fill the flask completely full of water, I could then use it with absolute immunity to drive that nail into that block. Why? Because water is highly incompressible, and the vessel would feel nothing. This would act like a solid hammer. Another consequence of Pascal and of Torricelli. Beautiful thing. I have a can here filled with water, and I hope you can see on a close shot that there is a hole in that can, and yet the water does not come out. And I say, that's fantastic. I'm going to pull out the stopper. Watch it. I'll give you evidence that there's water there. There it is. I put the stopper back in. The water has ceased running out. Question: what's holding it in? Obviously atmospheric pressure. Question, very important. How tall a can could I use to do this? Answer: 34 feet. Isn't that fantastic? Fantastic. Now, one more demonstration. One more. I have here a U-tube. A U-tube. That's a tube shaped in the form of a U. Mercury in the bottom part, water colored above it, and you see there is a difference in levels in the mercury columns. What will be the ratio of the water level to the difference in the mercury levels? Answer: 13.6, which is the specific gravity of mercury. And I invite you to do this experiment and wish you good fortune.